visible, sir?
Yes, sir.
Yes, sir. Yes, sir.
Okay, okay.
Yes.
So good afternoon to one and all. Where is the slide? So good afternoon to one and all. Today we're going to see about QT-03 basics quantum programming. Sorry about a little bit text alignment. I'm running from Google slide. In today's lecture, we're going to cover about from classical pixels to quantum circuits. So the topic is mainly involved with computer vision. Okay. So I want to acknowledge this entire session is based on the presentation originally created by Dr. Santosh Kumar Viparthi, professor from IIT Ropar. Okay. I thank him. With this permission, we're going to use this slide for educational purpose. So this is I want to say the disclaimer. So already we are doing computer vision. Why we want to do in quantum? Okay, so this is our topic. So I want to start with the author's point of view who created this slide. So we will try to cover from the basics. Right. So classical image processing is reaching its limits. So whatever we are doing using our CPU, it is not sufficient. So that is why we invented GPU, which will do graphical processing unit. Okay. So all our data is converted into matrix form, and we purposefully will do only matrix form of operations. Okay. So whatever we are doing using matrix operation. Okay. So each and every time we can use either 0 or 1. So this is the potential of classical computing, right? So we have only two options to perform over any kind of binary data. Okay. We need to do only binary operations, right? So each and every data, each and every sequential in pixel processing is based upon binary, right? So each and every process, it is handcrafted. So most of the time in classical image processing, we need to do hand-picked guidance for each and every segment, right? Initially, we need to train our model, right? What is the advantage of quantum? If you are using your visual data, maybe it could be audio, video, or image. It could be any kind of computer vision data, visual data. What is the advantage? You can create a quantum circuit and you can apply the rotational gases. You can change the phase shift. You can tilt. All this operation you can do simultaneously. Okay. So that you don't need to do each and everything sequentially. To compare how classical processing is doing and try to compare with quantum. So given point of time, you are able to compute a very large amount of data. Okay, so works on each pixel simultaneously to unitary matrix multiplication. So again, the same process we are doing matrix operation, but each and everything here we are doing in unitary matrix multiplication. So this is the only difference I want to highlight. Right, simultaneously we are doing, and we are able to simulate filters with entanglement patterns. So slightly some of our operations are entirely different from classical perspective. Right. So we try to look at from hardware point. Quantum hardware is maturing. So each and every year, quantum hardware is maturing. Okay. So take an example of IBM, Google, Quantum AI, Xanadu, okay, IonQ. So all these hardware manufacturers are focusing how to integrate their QPU along with their cloud service. Suppose if you are interested in quantum vision, computer vision, you can focus on quantum also. So this will give a added advantage in futuristic point of view. So all these platform will give access to the real quantum processor via cloud. We already know we did simulation, okay, and we are in noisy intermediate scale quantum era, which means whatever we are doing the experiment, it might contain some error, it might contain some inaccuracy. Okay, so we need to understand whatever we are able to do in classical, we cannot do the same level at quantum, but we need to scale it down. We need to take a toy level problem. As a beginner, as a researcher, what I suggest you always focus on how to implement the classical techniques in quantum at basic level. So whatever we have in our mindset, we need to let it down, right? So why we need to do image processing using quantum computing? So before doing any research work or research task, we need to ask this fundamental question. Already we are doing using classical resources. Why we need to go for quantum? Right? So if you want to do pixel manipulation, suppose if you want to do parallel pixel manipulation, okay, quantum system allows you to process all pixels simultaneously through superposition. Okay, so this is basic and fundamental if you want to do any image processing, right? Any image processing or computer vision, you need to apply superposition for all your qubits. Then only you are able to do simultaneous operation. So always it is good to know what quantum phenomena we are dealing with and where we need to use those phenomena. Okay. So what is the gate which will create superposition? Anybody able to answer? What is the fundamental gate we are using for superposition? Yes, exactly, Hadamard gate, but it will create equal superposition. Okay, superposition is any state within your Q sphere, but Hadamard gate will create exactly equal superposition. So for an example, the T gate, S gate, U gate, R gate, RY gate, RZ gate, all these gates will create superposition. But the question is, what kind of superposition state you need to go? What kind of superposition state you want to initialize? Okay, this is the fundamental question you need to know. So in quantum, it will operate on a superposition of all pixel position at once. So before picking the superposition, you need to decide whether this superposition will lead to parallel computation, right? In classical, process loop through each and every pixel sequentially. Even though we are doing parallel computation in classical, but take an example of image, it will process each and every pixel sequentially, right? So if you are using quantum algorithm to do your image processing, so the quantum algorithm will enhance future extraction. So each and every step, okay, it will be enhanced by quantum computing. Suppose if you want to extract future in classical image, okay, rather than classical, you can go for quantum, right? So if you're designing a quantum circuit, you can reveal non-local features or subtle patterns via entanglement. So we already covered what is the meaning of superposition. We need to apply superposition for each and every pixel. Okay, then only you are able to do simultaneous process. Same way, if you want to extract future, then you need to do entanglement. Okay, because entanglement will create some patterns. With the help of that patterns, you're able to identify some non-local features. Right. So 3 points you need to note. One is superposition, and we are doing simultaneously, and we are doing entanglement for future extraction. So this is how we need to correlate the quantum mechanism with our purpose. Okay, then only we able to decide which gate to implement in our circuit. So we already covered unitary operations. So this unitary operation will help you to do computer vision, right? Take an example of quantum gates like Hadamard gate, parameterized rotational gate. So RX, RY, RZ. So all these gates will help you to create superposition. Entanglement will create any changes simultaneously, right? So it will help you to identify patterns. Patterns are features in your image. So all these features have some correlation. So this correlation we able to extract through entanglement. Is that clear? Yes, thank you. So take an example of RX gate, RY gate, RZ gate. All these rotational gate will help you to create superposition, but it will not be equal superposition. So that is the point you need to know, right? So don't always think about Hadamard gate to create superposition. It, if you want only equal superposition, then go for Hadamard gate. So all these things we need to do in classical. Take an example of applying filters. If you want to do edge detection, if you want to do convolution, you can use unitary operations. Okay. So if you are entangling or if you are creating superposition, it will enable unique quantum operation, right? So this is what I discussed. So create entanglement based correlation between pixels. Okay, so each and every pixel has some correlation. Okay, so in image it is very obvious. So based upon the segment, based upon the region, based upon the region. Yes, I will explain, please wait. So based upon the region, correlation will exist. And this is limited to traditional operation. I will explain how to use entanglement with the coding. Just we will cover the theory part first. So take an example of bit, only two data, uh, either 0 or 1, right? In qubit, it will contain in between 0 and 1. So the coverage from state 0 to state 1. So whenever if you're using bit, it will be deterministic value. It will contain only a deterministic value. Wherever you are using qubit, it will contain probabilistic value. So each and every time the value will change randomly and dynamically. So sometimes you will do operation, you will put some quantum gates, your values will get changed. Sometimes automatically the values will get changed because of noise in your quantum hardware. Okay, so that is why the value existing qubit always probabilistic. So very random in nature. Even though if you are not doing any operation, slight variation will happen within your data, right? So normally the data represented either 0 or 1. Here it is the value represented in the form of superpositional state, right? So superposition we need to create. So initially all qubits are in state 0 or state 1, right? So what is the difference between bit and qubit? The better way you're able to visualize using qubit block sphere. Okay, if you have any quantum data, you're able to visualize each and everything in intermediate steps. So this will give a clear idea about how quantum algorithm works. So as a beginner, you need to know, right? So each and every time we will use classical logic gates, AND gate, OR gate, NOT gate, XOR, NAND. All these gates we try to manipulate our value. Okay, take an example of coin. Coin, you mentioned the head as 0 and tail as 1. And this information represented by only two states. Where in case of quantum, your data can be manipulated using quantum gates. So what is the purpose of your quantum gates? It will manipulate your quantum states. Right? Take an example of head state, okay, which is mapped to 0 state. So tail, which is mapped to state 1. So this is how we need to relate the physical phenomena into abstract quantum states. Okay, so qubit store information as probability amplitudes of its basis state. So you can choose your basis state. So here we chosen state 0 and state 1, right? So sometimes you can choose positive state and negative state. So based upon your basis state, you can represent your qubit information. Okay, take an example of block sphere. Now it is pointing to south pole, state 1. Okay, So QT-0 is a quantum state analogous to the classical bit 0 we already covered. This is quite refreshing. Okay, so QT-1 is the quantum state analogous to the classical bit 1. Okay, so if you want to represent in terms of probability of 0 equal to 100% whenever if you are in state at 0. So this is the meaning. So when you do measurement, what happens? The probability of 0 will become 100%. In case of QT-1, if you are doing measurement, what is the probability? Probability of getting value 1 is 100%. So in block sphere, obviously it is pointing to North Pole. So state 1 is pointing to South Pole. So mathematically you can represent QT-0 as 1, 0. So 1 in the uppermost hemisphere, right? So mathematically QT-1 is represented 0, 1. So the bottom of your circle, okay, the bottom part of your hemisphere has that component 1. So superposition is the fundamental quantum property that allows a qubit to be in combination of both state 0 and state 1 at the same time. Okay, so unlike classical, we already know all this stuff, right? So it is like superposition, it will keep on rotate, right? So when it is in superposition, we can separate into two independent states. Okay, alpha state head plus beta at tail. So try to remap in mathematical form. So this is your wave equation. Okay, your spinning coin is mentioned as psi. Okay, the action is represented in the form of a mathematical function. This is your wave equation. So whatever the dynamical system you are having, you are able to represent with the help of wave equation, right? So whether your QT-0, QT-1 are the basis state and alpha and beta are complex number which are called probability amplitudes. So according to the Bond rule, if you want to do, if you want to take modulus of the amplitude of state 0 and modulus of probability of a Schrodinger cat. So you can imagine cat is like a functional thing, right? And the superposition is divided into two halves. One is live state, the other one is dead state. And what is the probability of cat being alive? 1 over root 2. So apply the same logic over here. Apply modulus to the 1 over root 2. Okay, do square. Okay, take modulus and do square. You'll get 0.5. That is 50% of chance cats being in alive state. So entanglement is a quantum phenomena where two or more qubits become interlinked such that state of one instantly affects state of the other, no matter how far apart they are. It means there is a strong correlation exists between two quantum particles. Mathematically, okay, so if two coins are entangled, so whatever happens for one, observe, almost the unknown is also get affected, right? So as soon as if we are observing one asset, the other instantly become tail if it is opposite. So by refreshing superposition and entanglement, we can look what is a quantum parallelism. So quantum parallelism allows quantum circuits to evaluate, manipulate multiple inputs in a single shot, which will enable exponential speed up for some tasks. So sometimes if you want to increase your speed of your operation, you can go for quantum parallelism. Okay. So in such a way, So all these qubits need to be interlinked. So how you can create interlink between all qubits by creating entanglement, right? Suppose if you want to merge multiple inputs in a single stream, then you can go for quantum parallelism if it is possible, if it is needed. So take an example of classical computer which will evaluates one input at a time. Okay, f of 0, f of 0 1, f of 1 0, f of 1 1, right? In case of quantum, if you able to create superposition for inputs, it will process them at once using a single quantum circuit. So here there is a difference. So all these four input combination, what you can do, you can create the state function, okay, psi, right? Immediately it will do parallel process. Suppose if you have two qubits, if you are creating superposition and you are able to do entanglement with second qubit, it will do all process simultaneously. So quantum algorithm, the output is always not always deterministic. It depends upon the probability that come from the amplitude of quantum states. Okay. So what is happening during a quantum execution? Interference will happen. So interference is the key phenomena or fundamental concept happening in the quantum mechanics where probability amplitude combine together. So it is like similar to wave interference in physics. Waves can add, it will create constructive, or wave can cancel out if it is destructive. Okay, if it means a constructive, amplitudes add, probability will get increased. If it is destructive, amplitudes cancel, probability decreases. So everything we viewed as signals, everything we viewed as terms of probability. So this is a good link where you can use, where you can visualize interference. I'll share in the chat box. So go through this link, and they gave a beautiful explanation how interference is happening and how you can visualize interference. So this is what happens when you do modulus and if you do square, right? Measurement will create an interference. Right. So without interference, if you want to use quantum computing, it will be just random guessing. So that is why we need to use measurement at end of our quantum circuit. So measurement will create interference. It will interpret your result. Okay, otherwise you might ask, so everything is random in quantum, and then how we can believe quantum computation? Okay, so even though if it is random, you need to run for multiple times, n number of times. You need to have some patience. Okay, until the result is guaranteed, you need to execute the same experiment n number of times. So if you are running quantum experiments n number of sufficient times, it will help in increase the chance of correct answer, reducing the chance of wrong answer. Take an example of measurement. Whenever if you are doing any quantum experiment, if you are doing measurement, you will have different combination of outputs. You have different combination of outputs. So each and every output have amplitude. Each and every state, quantum state, have some amplitude. So whenever if you are doing measurement, okay, whenever doing any quantum operation, what happens? It will create constructive interference. If you are doing constructive interference, the correct answer amplitude will get increased. The height will get increased. Suppose if you are doing destructive, okay, the amplitude of wrong answer will get reduced. So here the blue color is correct answer. All remaining this pink is negative answer or wrong answer. Okay, the whole agenda of quantum algorithm, we need to create more constructive interference. Okay, and we need to do more destructive interference. So until you got the differentiable correct answer amplitude. So this is what we are discussing. We are dealing about quantum measurement, which will act like collapse of a wave function. So when a qubit is measured, it will collapse from the superposition to one of the basis stage 0 or 1 with the probability alpha modulus 2 whole square and beta modulus 2 whole square respectively. So after measurement, qubit is no longer in superposition. Okay. So it is like the coin is spinning. Whenever if you are doing measurement by your hand, you will get two probabilities or two possible states. So measurement is the bridge between classical world and quantum world. So measurement is inevitable if you want to extract useful information from a qubit. So sometimes you can see some experiment without measurement. It means it is theoretical. There is no real world use case if you are constructing a quantum circuit without measurement. Okay, only ideal cases you can use quantum experiment without using measurement, like a state vector simulator. Okay, mostly all the simulator will not exactly do measurement. Okay, measurement only happens in real quantum systems. Otherwise, it is based upon some model. So measurement is irreversible. So even though these are very basic concept, we need to go repeatedly. When you do measurement, what happens? The operation is irreversible. So once you do measurement, you cannot go back to original superposition. Once the wave function is collapsed, it is collapsed for forever, right? And the result after doing measurement, it is probabilistic, and you cannot predict the exact result, only the probability. So sometimes it could be the correct one, sometimes it could be the wrong one. So it is not like classical, right? So most of the time, the measurement will act like destructive. So most quantum measurement destroy superposition. If it is. So let's recall the quantum gates. Quantum gates are building blocks of quantum circuit, gate, not gate. So whenever if you apply quantum gates, it will rotate the star each the time in hyperspace, which is called Hilbert space. Okay. So quantum gates will not display amplitudes and phases of quantum states. So quantum gates will give additional computational ability when compared to classical. So that is why if you are doing computer vision, the previous slide, if you want to, I want to explain, you need to explain this slide. This state will get collapse and will get output in such a way. Either you will get value 0, value 1, like binary. So that is why measurement is always related to destructive. So it will collapse your superposition state. It will destroy your superposition state. So we'll cover some classical gates. We'll cover some classical gates. Take an example of NOT gate, which is 1-qubit gate. So you can recreate NOT gate in quantum, okay, with the help of single qubit. Suppose if you want to implement C0 gate, at least you need 2 qubits. Okay, so some gates have no classical counterparts. So these are classical counterparts. Okay, but take an example of Hadamard, it will create equal superposition. There is no example in classical for this. So take an example of NAND gate and compare with C0. Can you find any fundamental difference between NAND gate and C0 gate? How it is designed? Anybody able to answer? Can you find any difference, architectural difference between NAND gate and CNOT gate? Okay, we are getting combination of zeros and one. Any other answer? Qubit, okay. Any other difference you can find? Look at the gate architecture, number of inputs, number of outputs. Yes, reversible. Exactly. So in quantum, you need to always maintain how many inputs you are getting, the same number of outputs you need to create. So here you have two inputs, but only one output. Here you have two inputs and you have two outputs. So how many number of pins you have in input? The same ratio you need to maintain in output side also. That is why all quantum gates must be reversible, or all reversible. If there are some quantum gates, if it is not reversible, you need to create the alternative version. Take an example of S gate, T gate. So these gates are not reversible in nature, but you can create reversible gates using dagger. So are you able to recall? So these are single qubit gates. So whatever we covered, X, Y, Z, S, T, H, R, Z, R, Y, R, X. So these are single qubit. So C0, swap gate, all these gates are 2-qubit gates. Okay, so let's discuss about the quantum circuit, basic stuff again. Okay, quantum circuit is a sequence of quantum gates applied to qubits to manipulate their states and perform computation. So most of the time, it is very and we are doing the same stuff. Okay, we are training our model, we are giving some reward in order to narrow down our solution space. Okay, so everything we are doing in quantum also. So this is a gate, quantum gate. So we are initializing over here, and we are having some rotational gates. Okay, so we are creating some control not gate, right? So this will create interlink between your qubits. So in a quantum circuit, qubit pair represents the state of each qubit over time. So each and every gate will act according to the timeline. So here timeline is very important in quantum, right? We'll see what it means. Okay. So at the end, what you need to do, you need to do measurement to extract classical output. So this is the basic architecture of any quantum circuit. So let's discuss in detail. Okay. So initially, you need to prepare your qubits. Okay. This is your initial quantum state. Then what you are doing, if you have any inputs, we need to embed using rotational qubits. or rotational gates. Okay, so this is where we are embedding our input into quantum bits. So you can ask, instead of creating the initial qubit, we can go for directly embedding. Okay, we cannot do because the qubits are in random superposition. So you cannot directly embed your input qubits. So before embedding, what you need to do, you need to initialize your qubit. It could be either state 0 or either state 1. So it is always advisable to initiate your qubits. Then you go for embedding process. Right? So once you gave your input, embedded your input, then you need to vary your quantum state using rotational gates. So this is called variational quantum circuit. So most of the time you studied only quantum circuit, which is static. Okay, no more operation is happening. But here, each and every time the values are get changed. Okay, like a repetitive loop, repetitive process. So if your circuiting is doing a repetitive variational values, then you can coin that circuit as variational quantum circuit. So finally, you need to do measurement. So this is the basic architecture. If you're looking over here, okay, so all these operations are repeatable. The variational quantum circuits, you can change your value until your measurement. But when you do measurement, you cannot vary your inputs. You cannot change your values in your quantum circuit. So everything is viewed in the flow of time instead of space. Are you able to understand this slide? Any doubts? Any doubts you can put in chat box? If gates are reversible, then why superposition is irreversible? Superposition is reversible if you are doing, but if you are implementing Hadamard gate, you don't know where it will go. Once you do measurement, it is irreversible. Superposition state is not irreversible. Superposition state is reversible. Take an example of Hadamard gate. Okay, from stage 0, if you are applying Hadamard gate, it will go to positive state. From positive state, again if you are applying Hadamard gate, it will go back to stage 0. Are you able to get the idea? So superposition state is reversible. If you are doing measurement, see, if you apply, if you are in stage 0, imagine if you are in stage 0, if you are applying Hadamard gate, okay, if you are applying measurement, either you will get 0, either you will get 1, you don't know the result, which is truly random in nature. Okay, but if you apply stage 0, if you apply Hadamard gate, it will go to positive state. From positive state, if you are applying Hadamard, it will go back to stage 0. From stage 0, if you are doing measurement, what you will get? From stage 0, if you are doing measurement, what you will get? Are you able to get my question? My question is, from stage 0, if you are doing measurement, what value you will get? What value? 0, that's all. Because the state is known. The state is known. Exactly. Thank you. Thank you. So in this quantum circuit, we need to change our parameter. So these parameter are tunable. We already covered 2 angles in the block sphere. So try to recall. Okay, these 2 parameter used in optimization task. Suppose if you want to do optimization, what you can do, you can vary this delta and psi. Okay, it will typically train like a neural network. So if you are already working in neural network, you're able to understand these parameters are tunable, changeable, variable. Okay. So the variational quantum circuits will act like neural networks for quantum computing. Yes, these are our own choice. We need to understand our problem. We need to select our rotational gates. Yes. And why we are using this? Because it will combine quantum computation, take an example of parallelism, entanglement with classical optimization. So if you are using variational quantum circuit, you need to do quantum computation and also classical computation. So some part you need to use your classical system, you need to optimize your result, then you need to give feedback to your quantum circuit. So actually it is a hybrid approach. So if you are using VQC, it is a hybrid approach, right? So take an example of this circuit. So initially what we done, we are doing qubit initialization stage 0. Then we are implementing some rotational gate. Again, we able to train our parameter by using rotational gates. So initially we are using RZ, then RX, then we try to create control knot, then we try to create the series of RY gates. So the entire this section, which is highlighted in red rectangle, okay, which is parameterized quantum gates. So each and every time we need to train this parameter by changing these values, right? So the first step after creating your quantum circuit, we need to embed our data. So embedding data is like loading data into the quantum circuit, right? So how we can embed data? So it is like classical embedding, like images, vectors, labels, we can able to give for your quantum states. So one particular example is angle encoding. Suppose you have started with stage 0. So next layer RZ. So here we are doing some rotation. So this is RZ gates. RZ gate means it will do Z operation, okay, according to your angle. So angle is important over here. So according to your angle, it will do manipulation of your stage 0 state. Okay. So quantum circuit can only operate on quantum state, not on classical data. So that is why we need to start with quantum state. So the first example is basis encoding. Okay. So basis encoding maps classical bit string directly into quantum basis. So what are the quantum basis state we have? What are the quantum basis state we have? Not 0, 1, sir. State 0, state 1. Yes, kit 0, kit 1. Any other basis state? Any other basis? Kit plus, kit minus, kit I, kit minus I, right? So all these you need to use kit or state before that. Otherwise, we'll get confusion between classical and quantum, right? So each classical value becomes a specific computational basis state of a qubit system. So whatever the basis state you are picking, you need to convert all these classical value correspondingly. Take an example of binary string. Suppose if you have a binary string 101, you can directly map to a quantum state in such a way that, so in quantum 101, you can represent in kit 101. Okay. So you can view like a tensor product. You can view this operation like a tensor product. Okay. So whenever if you have more than one qubit, each and every time it will do tensor product. So this is the physical view, this is the mathematical view. Okay, so no rotation, no superposition needed for this operation, just assigning binary state to qubits. So sometimes without doing any quantum gate operation, we can embed your data. Okay, so use cases, you can create quantum logic circuits. If you want to design oracle, if you want to do decision problem, we can use binary encoding or data encoding. So we will have some coding example for this. This is not practical. That is why we are taking toy problem. That is what I told initially. We cannot do full-fledged classical image processing in quantum. We can give you a try. Yeah, thank you. So it will give yeah additional perspective of how you can do encoding. Maybe I will zoom it for your convenience. Okay. So how many basis state we have? Ket 0, Ket 1, right? Not 0 on 1. If you're saying 0 on 1, it becomes classical, right? So you can pick your basis state according to your choice. Now we are selecting Ket 0 and Ket 1. Okay, I'll share this Jupyter notebook for you. I'll share this code. Suppose if you are having cube rate, try this code. My code is missing. Sorry about that. I'll check my repository. Then we can go for the next example. I'll share this basic encoding later. Okay. So next example is angle encoding. Okay. So angle encoding is a quantum data embedding method where classical value are mapped to rotational angles. Okay. Take an example of RX gate, RY gate, RZ gate. So these gate will try to alter your quantum states. Suppose if you have a data value called x, so x is your classical data, then what you can do, you can apply RZ gate in order to get the quantum superposition state. So this is an example. Okay, so this is the matrix form. So before dealing with any quantum circuit, before doing any operation, mathematically you need to know what operation you about to do. Okay. So this is an example for classical feature vector. So each x contains a variable values, a set of values. Okay. So how to create each and every feature using quantum gate, using RZ gate. So give your input x0 for RZ, okay, which is multiplied with stage 0, and you'll get this quantum superposition. This is not equal superposition. This is just superposition. Are you able to get the idea? Are you able to get the idea? Yes. For visualization, I try to open block sphere, group blotch. So I'll share this link with you. Already share, even though I'll share again. Now it is in stage 0, right? If you're applying Hadamard, you'll get equal superposition. Okay, so click 0, click Rx. Now whether it is in superposition or not, click stage 0, click Rx. It is in superposition. That's all. Again click Rx. It will do rotational change respect to Rx gate. Again Rx. Again Rx. Rx. So this will give a finite transformation about your angle equal to pi by 8. Okay. To reach from stage 0 to equal superposition, how many Rx gate you require? Rx d equal to pi by 8. Can anybody answer? 4. Exactly. So click stage 0. One, two, it is already in superposition. So anywhere in your Q sphere, it is already in superposition. So click stage 0, click RZ. So nothing happens. Okay. So you need to know where this Rx works, RZ works. So take an example of state 1, apply RZ gate. Changes happening only in phase. Are you able to see downside of this block sphere? Changes happening, but not physically, only in phase wise. So this will create changes in your phase. So click 1, apply RY gate. Now you can see physical change. Which is no, I am not talking. Just now I stopped. So take an example of an image, 2 cross 2 image, okay, which contains these many combinations, right? So the first step is we need to normalize pixel value from 0 to pi. So how we can normalize? Okay. we need to take each and every pixel and we need to map to rotational angle theta. Okay. By doing so, each and every time the theta is multiplied with your input x divided by 255 because that is the maximum possible combination, then it is multiplied with pi. Yes, I can give 3 minutes break and we will join.
Meanwhile, if anybody is having any issue of not able to take QT-03 quiz number 1, right? Please try to inform me so that we will permit you to write. Few requests have come. All those who have requested, please take the quiz. Quiz number 1, right? It is open till today. So you take the quiz, we'll consider that. 894 people have already taken. So if some of you also take, we hope that we'll cross 900. And similarly, around 820, 830 people have taken quiz 2. There are about 60, 70 people pending. So please check if there is anybody, please take the quiz. The quiz is open. Quiz 2 is open till today night. Quiz 2 is open till today night. Quiz 3 is open till tomorrow night, right? So please finish the exam by around 12 o'clock tomorrow. Then we will issue the certificates at 4 o'clock tomorrow, right? So please, first set of certificates we are planning to release. Your names, one email has come to all of you to check your names. Please check your names and please revert back so that once we are taking those changed names, we are finalizing that and we are going to give, we will use the data for issuing the certificates. So we will create the certificates and issue it tomorrow. So please try to help us by doing this, right? We request you to kindly cooperate in this matter. One is certificates, one is quiz 1. If still anybody is left out, or there was some problem in not able to, while writing, there was any problem, that's all. This is for people who need a second attempt. First attempt we are not opening, but if there is any such request, please let me know. Let's see what best we can do. Quiz 2 is tomorrow. Today in night is the final time, 11:59, midnight. Before midnight, you take the exam. Quiz 2, quiz 3. Till tomorrow midnight it is there, but if you take the exam by 12 o'clock, we hopefully want to give the certificate tomorrow. By the time the course is over, you will get the certificate as well. By 4:30, we are trying to issue the certificate. So thank you so much for all your efforts. And Radhakrishna, we are ready? Yeah. Yeah, somebody has. Okay.